anytime you want to start.
Okay, so we're talking today about electrical, and specifically electrical as it applies to air conditioning. And we want to go through some things on electrical that follow safety first, because we're always going to follow safety first. And in this case, we're going to talk about the fact that we deal with voltages that can hurt us. We deal with 240 volts quite often. We deal with 120 volts, which is just as deadly. And we deal with lower voltages from our transformers. So we're going to be voltage conscious, and we're going to be careful, and we're going to test before we touch. So I want to show you a little prop that we continue to show, but we just want to make sure that you stay aware of the fact that we're always going to talk about safety and the fact that it can kill you. You don't want to be shocked through your heart. You don't want to be shocked ear to ear, and even on your arms, as we've discussed before. Wet skin versus dry skin is just not a good thing to do. So we're going to stay conscious of that. We also want to talk about the fact that we're going to have units. This is a condensing unit. We're going to have units open. While we're working on them, they will be open. They'll be exposed. Sometimes they'll be locked out with electrical, and sometimes they'll be energized because of the type of testing we may be doing. If we were to walk away from a unit that we left open and energized, and a child or possibly a pet at the homeowner's place came up and put their hands in it, it could be deadly. So we have to make sure that we secure the work site. It's our responsibility once we open this equipment up that we secure it, we don't leave it open, that we manage it properly, and we also protect ourselves as well. If we turn this off at the breaker and we walk away, or we turn our back and the customer doesn't realize it, or the wife or the husband comes home and there's no air, they flip the breaker back on, you might have your hands in it. So there's lots of reasons for you to want to secure that. There's lockout, there's tag out procedures, there's all sorts of special devices you can use to secure electrical. On top of that, a lot of our disconnects are actually removable. Take it out, put it in your tool bag, take it with you, protect yourself. You're going to be wanting to check that voltage, and you're going to want to check it with a meter so that you know if you actually did turn off the right breaker. And we're going to get a meter out, and just a common volt-ohm meter. But how do I know the meter works? The meter's been riding around in my truck. The display might turn on when I go to use it. It might check. It might tell me 0 voltage. Well, that's not good enough. I need to verify that. I need to check my meter against a known source. Maybe I'll walk over to a wall outlet, or maybe I'll walk over to a unit that's running, or before I turn the power off, maybe I test this meter. I also can get inexpensively a proximity tester such as this one, which I can turn it on. I can keep it in my pocket when I need it, and I can hold it up to anything energized. If I hold it to any sort of power source that I'm wondering about and it goes off, it tells me that it's charged. And that's a second device telling me that I might need to check it again. So the point being is we always verify, and we double verify so that we're safe. While we're talking about safety, let's talk about attic conditions. Electrical, of course, is important, but equally important is the fact that we're in attics that are very hot. And I just want to point out the fact that the day you start the job, it could be possibly cool or not so hot in the attic. By the time you get back with the motor or whatever parts you might need, that attic may now be well over 100 degrees. And if you haven't properly hydrated yourself, you could suffer medical issues. So hydrating yourself doesn't mean that you get very hot, you run down and buy yourself a Gatorade and you're going to be okay. Hydrating means you started last night and you prepared and you drank plenty of water and you got your body fully hydrated. And your day today, the day you're working, is going to be much better, and you're going to be in much better shape tomorrow because you hydrate properly. So just pay attention to that. Remember, in the attic, you will be sweaty. Your arms will be sweaty. You'll be leaning up against equipment. We showed Shockman. We talked about the fact that it's more dangerous when you're wet. So you're going to be in the attic. You're going to be working around voltages, and you're going to be sweaty. Let's be very careful. Let's not crawl into an area where we're likely to get shocked. When we do get to an air conditioning unit and we're going to make that service call, most likely it's going to be electrical. And I'm going to say probably 80% of the time it's going to be an electrical problem. Of those electrical problems, a lot of times it's going to be this. It's going to be a capacitor. This is a very common failure item in air conditioning. Most of the time you're going to show up, and if it's an August day and I'm walking up, I'm thinking most likely a capacitor. I've already talked to the customer. I've kind of got clues of what it's doing, so I'm going to keep these. If I don't have this particular one, of which there's hundreds of different kinds, I could get multi-capacitors. And by using jumpers, these capacitors can replace 200 or 300 of these. So it's a very common thing to have on your truck. They also will fail. And when they fail, sometimes it's very easy to tell. You can see right here it's bulging. And that's a sign that it's overheated. It's time to be replaced. Sometimes they fail because they just get old and they start wearing out. And this one, even if it wasn't bulging and bad, it's rusted to the point where it needs to be replaced. So all of these have their reasons that you might use them or replace them. I've opened one up here so you can just kind of see inside. It's not very magical, but it is a foil sheet basically that's wrapped around a core, separated by insulators. It's a battery of sorts. It's a battery that holds a little bit of a short duration of voltage, but it is a high voltage. So before I was going to handle any of these with my hands, I have to make sure that there's no voltage here that's going to shock me and hurt me. The minute I take it out of the machine, it could possibly still be charged. So before I touch it, I'm going to take my screwdriver and I'm going to short these out to one another. And you can use a resistor, and there's other methods you can do it, but this is what you're going to have in your truck, most likely in your hand, and this works fine. That's what I would do. So let me move these out of the way and show you a circuit card which has some of its own issues. They fail. Circuit cards fail. And when they fail, it's usually because they've overheated or a lightning strike. I would say lightning's very common, or else there was an installation or a service issue that caused it. If we can remove this cover, and I can tilt this up, you can see this is a printed circuit board. This is a very delicate piece of equipment. If you notice, it's sitting on a bag that it came in. This is what they call an anti-static bag. And the reason is this bag protects this circuit card from your hands. You have a static charge in your body, and if you walk up and you just start handling this card, you very likely are going to kill these electronics in here. So they come in the bag to protect them. Before we take them out of the bag, we want to ground ourselves. We want to eliminate the electric charge that may or may not be in our body. Different times of the year, we have different charge issues, especially in the wintertime. So we're going to touch something metal, some sort of metal component that might be in the attic. We want to ground ourselves, get that charge out of us. Circuit cards are not always easy to diagnose, but they do try to protect themselves. If you look on this one, there's a fuse, similar to what's used in cars. And if you're lucky, the fuse blows first. The fuse goes, you get a new fuse, you pop it in, then you find out the reason it blew. It could be multiple reasons. The dog chewed the wire, the homeowner snipped it, the thermostat was bad, whatever. Look at the back of this circuit card. You can see where it's clearly burned. This one is 100% bad. Nothing to do but to throw it away, buy a new one, and start over. Most likely you're going to get a universal one, and you read the instructions, you'll get it in there just fine. So while we're talking about the circuit card, let's talk about some things that operate the circuit card, namely the thermostat. So I've got a couple of examples here just to show. This one, while fairly inexpensive, is electronic, very accurate, very easy to use, has built-in backlight, kind of nice. This is more old school, more of the older type, very simple, not much to fail, but also not very accurate. You may find these, it's just a switch. You can probably hear it clicking. Either way, there's not a lot of magic in the thermostat. Pick one you're gonna like. I like the electronic ones. They seem to hold temperature of the house much better. The thermostat is the brain of the air conditioning system. I have a prop display set up here for you to see, and with this we're going to show you how the thermostat is the brain of this system. So I want you to imagine that this component right here is the outside unit. This would sit outside of your home, and it has its own power cord. It's going to be connected to 240 volts on most cases that goes to this contactor, and nothing's happening. Even though it has 240 volts, nothing is going on there yet. And then this component, imagine this being inside your home, and this would be the part that blows the air through your house and sucks it through your filter and has the coil that provides the cooling. And that's what's connected to the thermostat. It also has a float switch right here. So I want you to see is that this is powered up, the outside condenser unit is powered up, neither one is doing anything because the brain, which is the thermostat, has not told them to do anything. So if I look over here and I just simply switch it to fan, my indoor fan is going to turn on. When that fan turns on, I start filtering air, I start moving air through the house, but I'm not cooling any air. In order to cool, we have to have the outside unit running. If you notice this small wire connecting the inside unit to the outside unit, this is what's going to tell the outside unit to run. So if I switch over to cool, now we've energized our fan, so we're moving air across our coil through our filters. We've energized our outside unit, so we're starting to cool, we're starting to remove heat. If we had a problem in this house and we started getting water in our float, in our drain pan, before it got into our ceiling, the float switch would raise up. And as you can see, the indoor fan kept running, but my outside unit went off. When that outside unit turns off, I stop making water. Even though the fan's still running inside, we're no longer making water. So the float switch did its job, turned off the outside unit so that we didn't have damage. So we'll push that out of the way, and I want to show you a transformer. And I'll pull one out here and put it up on the board. So here we have a transformer. It's the same thing you're going to see inside an inside unit of any air conditioning system. And then we have the contactor, the same one you just saw connect over here, the same one that lives over here in the condensing unit. Very common air conditioning contactor. When I energize this by plugging it in, we did pull the contactor in just now. And I'm going to show you why. When I get the meter, turn it on, get my safety glasses on. Okay, put this over here so you can see it. Right there. What we're going to read is the voltage that's going into the transformer, which is up here on the top. And if I read it here, we should be seeing that we have at least over 100 and say 20 volts or so. If I read what we call the secondary side of the contactor, that's our control voltage. That's going to be a lower voltage. It's going to be most likely 26 or 27 volts on the meter. That's what's going to be pulling in our contactors. That's the safe voltage that we work with. So the primary side up here, we have our 120. The transformer's job is to take 120, turn it into 24, and we do that here. As we can see, if I disconnect the power to the transformer, our contactor is going to open back up. Let's move this out of the way. And this talk about a helpful hint that might help you quite a bit. Say you wanted to replace that contactor that we just talked about, and you didn't take this picture. The picture that I have over here on this side is the before picture. This picture would be after I replaced the contactor. If I did not take this picture, it's going to be very hard for you to wire this back up. So take your phone, take a picture with your phone before you remove any wires. It will make your life much easier. While you have that phone out, take a picture of the model number of the unit, the serial number of the unit, maybe any other particulars about that unit that might help you later. So with electrical, we're doing diagnostics, and we can take a meter and we can diagnose for hours. we can come in here with the meter and we can get up in this machine and we can check every single component on this machine. We can check contactors and we can check capacitors and we can pull them out and we can do all sorts of diagnostics. But what I recommend we do first is the most simple thing. And we always want to do the simple things first. Go to the thermostat. This makes sure the thermostat is on. And believe it or not, that happens more often than you think. A customer will just simply forget to turn the thermostat on. So you're going to get to the house and you're going to spend an hour out here diagnosing this unit that's just a thermostat not switched on. They're not going to want to pay for it and you're going to feel a little bit foolish. Now this say you turn the thermostat on and the unit doesn't come on. Now we're outside at the unit and we've taken the cover off and now we need to diagnose why isn't this unit running. The same thing. I can start checking these components with my meter one at a time consuming, or I can start eliminating process. I can come to the contactor, I can energize it. Immediately with that one press, it just told me that most of these components are probably okay, that my problem is somewhere else. So now logically, I'm looking at my contactor and I'm wondering, why isn't it pulled in? Because when it pulls in, everything runs. So now I simply just need to check voltage here at the contactor. If I have it, I just need a new contactor. If I don't have it, then I'll start going backwards and I'll see what the problem is. It could just be that float switch that we talked about earlier. It could be something that simple. So what I want you to take away from here is be very efficient in your diagnostics. Use your knowledge of how the system works. Use things to your advantage that eliminate whole areas of the unit. If the thermostat turns the unit on, there's no reason to check for voltage to the unit. It's there. If the fan runs, there's no reason to check the contactor. It's pulled in. So use those things to your advantage, and you'll be much better at diagnosing.